Hello everyone. So welcome to lecture 16 on numerical analysis, paper 2 of BSc 5th semester. So in the last few lectures we have seen what is a solution of system of linear equations. In that we have seen solution of simultaneous linear algebraic equation. So only we have concentrated on iterative methods. So when the system is solvable by iterative method, so this is the condition that is diagonally dominant, and we have seen Jacobi iteration method and how to solve the given system by Jacobi iteration, solving system for x, y, z, and go on iterating using initial values x0, y0, and z0. Okay, and we have also seen an example of Jacobi iteration. So after solving an example of Jacobi iteration, we have moved to the Gauss-Seidel method. So in the also we have seen the Gauss-Seidel method, how to solve a system of linear equation using Gauss-Seidel method. Okay, so this is a given system and it should be diagonally dominant. So then solve for x, y, z using the equation 1, 2, 3. So we have to use x0 and y0 and z0 in the first iteration only, that is while finding x1. And while finding y1 we are going to use the latest root of x, and while finding z1 we are going to use the latest roots of x and y. So this way this Gauss-Seidel method continues, and this procedure is continued till the convergence is assured. So we have solved the same method by Gauss-Seidel method, same problem by the Gauss-Seidel method, and we have obtained a solution in very few steps. We have also seen Jacobi iteration method, Gauss-Seidel method, and what is the difference between Jacobi iteration method as well as the Gauss-Seidel method. So I hope you have followed this difference. While finding x1 there is no difference. While finding y1 in the Jacobi iteration we are still using x0, while in the Gauss-Seidel we are replacing it by x1. Same difference with the z1. While finding z1 in the Jacobi iteration we are using x0 and y1. Okay, while in the Gauss-Seidel we are using the latest x1 and y1 as a initial values for z. Okay, so we have solved the same problem by Gauss-Seidel method also, and we have obtained a root which is converged to fourth iteration itself, corrected to 2 decimal places. And we have seen example 3 by both Jacobi as well as Gauss-Seidel method. So we have solved it by Jacobi method as well as Gauss-Seidel method. Okay, so this is a table of iteration for Gauss-Seidel. So we have seen 3 examples so far. So this is by Gauss-Seidel and this is by table of iteration. Here we got the convergence only at the 5th iteration itself. Okay, so we have derived a conclusion that Gauss-Seidel method converges faster than Jacobi iteration method. Yeah. So now in this 16th lecture we shall see the 4th example on iterative methods. Okay, solve by Gauss-Seidel method the following system. Solve the following system. Solve the following system by Gauss-Seidel method. This is a CI method. Okay, yeah. So what is the system given? System given is 28x plus 4y minus z equal to 32, x plus 3y plus 10z equal to 24, 2x plus 17y plus 4z equal to 35. Okay, See, by seeing this system, we see that here y term is little low, so we can exchange these two. And then the coefficient matrix becomes diagonally dominant. Then we can solve the system very easily. Okay, so therefore we go for the solution. So in the solution, see here diagonal elements are not dominant. In the given system, of equations, the coefficient matrix is not diagonally dominant. The coefficient matrix is not diagonally dominant. Okay, so therefore we need to make this as a diagonally dominant. So we rearrange as so that we are going to rearrange the given equation as 28x plus 4y minus z equal to 32. So this is z. So we change these two equations. Okay, so then I bring 2x plus 17y plus 4z equal to 35. So next x plus 3y plus 10z equal to 24. So now you can see that this is diagonally dominant. Okay, so this is diagonally dominant. Okay, yeah. So now we can proceed with the iteration method, right? So this is diagonally dominant. This system is diagonally dominant. So therefore we go for iteration. Therefore we proceed for Gauss-Seidel method. See, always this condition is necessary. You can see that mod 28 is greater than mod 4 plus mod 1. Okay, and mod 17 is greater than mod 2 plus mod 4. Similarly, mod 10 is greater than mod 1 plus mod 3, right? So therefore this is diagonally dominant. The coefficient matrix is diagonally dominant, therefore we go for the iteration method. So now, so we first solve for x, y and z. So therefore from equation 1 we solve for so hence we solve for x from equation 1. So from this we calculate x. So this gives x is equal to 1 by 28 into 32 plus z minus 4y. Okay, and from second equation we get for y. So y is equal to 1 by 17 to 35 minus 2x minus 4z, and z is equal to, from third equation we get expression for z, that is z equal to 1 by 10 24 minus 3y minus x. Okay, so now we treat this as equation 1, this as equation 2, and this as third equation, right? So now we go for the solving by Gauss-Seidel method. Remember, this is by Gauss-Seidel method. So therefore we need to have an initial value only y and z. Setting y0 equal to 0 and Z0 equal to 0. So we get the first iteration. So we are going to solve the first iteration. See, in the Gauss-Seidel method, we take only y and z zeros while calculating the first iteration. So first iteration x1. So x1 is what? So 1 by 28 into 32 plus z0 minus 4y0. Okay, this is minus 4y, right? So we use y0 and z0 to find x1. Okay, so this gives how much? So 1 by 28 into 32 plus z0 is 0 minus 4 into 0, that is 0. So this gives how much? 32 by 28, 1.1429. Okay. So next, while calculating the y1, we are going to use the x1 and z. So y1 is 1 by 17 into 35 minus 2 into what is x1? 1.1429 minus 4 into z0, that is 0. Okay, so this gives you 1.9244. So while calculating z1, so we are going to make use of both x1 and y1, that is 1 by 10 into 24 minus 3 into y1, that is 1.9244 minus x, that is 1.1429. So this gives you 1.8084. So this is the first iteration. Similarly, we now go for the second iteration. So for second iteration, we are going to use again y1 and z1. So while finding x2, we are making use of y1 and z1. So 1 by 28 into 32 minus 4 into 1.9244, that is y1, plus 1.8084, that is z1. So this gives 0.9325. So now to calculate y2, so we are going to make use of x2 and z1. So 1 by 17 into 35 minus 2 into 0.9325 minus 4 into 1.8084. So this gives you 1.5236, right? So next we go for finding z2. So while finding z2, so we are making use of x2 and y2, that is 1 by 10 into 24 minus 0.9325 minus 3 into 1.5236. So this gives 1.8497, right? So till now the root has not been converged. Therefore we go for the third iteration. So the third iteration, order to find x3, we make use of y2 and z2 to find x3. Yeah. So x3 directly I am going to write without those expressions. So x3 gives you 0.9913. So y3, while calculating y3, we make use of x3 and z2. Okay, so this gives 1.5070 and z3 gives 1.8488. Okay, see now the after the third iteration, so compare x2 and x3, so 0.93 and 0.99. Compare y2 and y3, 1.52, 1.50. So if you go for one more iteration, we may get to the clearer roots. Therefore we go for the fourth iteration. So I take it here, fourth iteration. So in the fourth iteration, while calculating x4, make use of y3 and z3. So this gives you 0.9936 and y4 is 1.5069 and z4 is 1.8486. See, in the iteration process, you just need to write the first 2 or 3 steps like this, right, in the detailed manner. Later on, you can just write these values itself by using the calculator. Then it is acceptable. Okay, even in the examination, after writing 2 detailed steps. See, first iteration we have written detailed steps, and in the second iteration we have written detailed steps. See, after second iteration we can go by this. Third iteration, fourth iteration, just use the values of x's. Okay, then it is acceptable even in the examination point of view. So no need to worry about this. So now we need to find out the fifth iteration in order to obtain the more convergence of roots. Okay, see, already up to 2 decimal points it is obtained. Up to 2 decimal points the root convergence has been obtained. Suppose if you want more convergence, that is up to 3 or 4 decimal places, then we need one more iteration, that is fifth iteration. So go for x5. While calculating x5, use y4 and z4. This gives 0.9936 and y5 is 1.5069 and z5 is 1.8486, correct to 4 decimal places. So now compare this y4 fourth iteration as well as fifth iteration. So compare now. So this is x4 is 0.9936 and x5 is 0.9936. So therefore we got approximately equal roots. So y5 is 1.5069 and it is also 1.5069. z4 is 1.8486 and it is also same. So therefore we can say that the root has been converged. So therefore, since the xyz values in the fourth and fifth iteration are same, therefore we can stop the iteration process here and we can conclude. Hence x value is what? 0.9936 and y value is 1.5069 and z value is 1.8486, corrected to 4 decimal places. Corrected to 4 decimal places. Okay. So this is a very easy method, but one need to be very careful while using the first iteration. In the first iteration, we are just using y0 and z0 in the x1. Later in the y1 we are using x1 and z0. So this is x1 and this is z0. Okay, initial value for z. In the z1 we are again using the x1 as well as y1. So this is y1 and this is x1. Okay, so if you just carefully substitute these two values, okay, then the iteration is fine. So we have solved the given system. This is the given system of linear equations and it is diagonally dominant. Therefore we have solved for xyz, and with the initial value y0 and z0 we have started first iteration and then moved to second iteration and seen third, fourth and fifth iteration, and we have seen that the fourth iteration and the fifth iteration are almost the same. So therefore we have concluded that the xyz values are this corrected to 4 decimal places. Okay, so this is one of the easiest problem. So this we have solved by Gauss-Seidel method. So next one more example we shall take and we shall see that example with both the methods. Okay, so take that example number 5 I think. So this is example number 4. So example 5. So this one we shall solve by both the methods. Solve the system of equations by by Jordan and Gauss-Seidel method. Sorry, not Jordan, Jacobi equation. Okay. Solve by Jacobi equation and Gauss-Seidel method. Okay. So what is the system given? The system given is like this: x plus y plus 54z equal to 110, 27x plus 6y minus z equal to 85, 6x plus 15y plus 2z is equal to 72. Yeah. So now looking at the system of linear equations, the given system, we see that this is not diagonally dominant. Okay, this is not diagonally dominant. Okay, so now how to make this diagonally dominant? If you change this to here, it becomes 26, and if you take this as second iteration, then it becomes 15y, and next z is the coefficient of z is 54. Okay, it is much more. We can take it as a third iteration, so we can take this as third equation, and this as first equation, and this as second equation, and we rewrite this. Then we can see that the system will be diagonally dominant. Then we can proceed to the iterative method. Okay, solution. So as the coefficient matrix of above system is not diagonally dominant. So we therefore rewrite it as below. Okay, we are going to rewrite it as below. So first will be 27x plus 6y minus z, which is equal to 85. The second will be 6x plus 15y plus 2z, which is equal to 72. Okay, and the last will be x plus y plus 54z, which is equal to 110. See, now we can easily observe that this is diagonally dominant. This is diagonally dominant. So the given system is now, the system is now diagonally dominant. Okay. So now we can start the iteration process. So solving for xyz, we get solving for x, y and z, we get. So from the first equation we solve for x is equal to 1 by 27 into 85 minus 6y plus z. Okay, and from the second equation, this equation we solve for y. So 1 by 15 into 72 minus 6x minus 2z, right? So from the third equation we solve for z. This is 1 by 54 into 110 minus x minus z, sorry, minus y, because we are solving for z, then it should be y here, right? So we treat this as a first equation, this is now second, and this is third. Okay, so now we set all set for iteration process. So only we need to choose initial values x0 and y0. See, first it is asked for Jacobi iteration as well as Gauss-Seidel. Okay, so first we shall solve by Gauss-Seidel, sorry, Jacobi iteration. So this is for Jacobi iteration. Okay, up to nowadays we can take it here instead of here, so we can take this to the next line. Okay, because up to this step for both Gauss-Seidel and Jacobi iteration it is same. It is same. Okay, right, we can take here. Okay, so now this is for Jacobi iteration. Okay, for Jacobi iteration, take x0 as 0 and y0 as 0 and z0 as 0 in 1, 2 and 3. In all the equations we need to take x0, y0, z0. So then for first iteration, so it is going to be x1, so we need to use for first iteration we need to take here y0 and z0. Okay, so what is the value of that? So 1 by 27 into 85 minus 6 into 0, because y0 is 0 and z0 is 0. So 85 by 27, this gives you 3.1485. Okay, similarly calculate y1. So y1 gives you 4.8 and z1 is 2.03704. Okay, so now immediately after finding x1 y1 z1, so before proceeding to means we go on proceeding with the second iteration, third iteration, so on. So I would like to have a table of iteration now. I would like to have a table of iteration. Table of iterations. Okay, so now number of iteration. So x values, y values, and z values. Okay, so in the first iteration, what is the x value? Is 3.1485, y value is 4.8, and z value is 2.03704. Okay, so next in the next we go for the second iteration. In the second iteration, we'll be having a x value as 2.15693, y value as 3.26913, and z value as 1.88985. Okay, so please calculate, please check yourself. I just give the values of the iteration. Okay, because it is a routine task, okay, nothing new in this. You just have to substitute the values of x0, y0, z0 in the first iterations. In the second iteration, use x1, y1, z1. Okay, so third iteration, this is going to be 2.49167, and this is 3.68525, and z value will be 1.93655. So please check. Okay, because I will not be doing in detail. Yeah, this is a routine task. You carry out the iterations. So in the fourth iteration, it is going to be 2.40093. Y value will be 3.54513, and z value will be 1.92265. Okay. In the fifth iteration, the x value will be 2.43155, y value will be 3.58327, and z value will be 1.92692. Okay, yeah. Now see that the root has not been converted, so therefore let us go for the sixth iteration. The sixth iteration, x value is 2.42323, y value will be 3.57046, and z value will be 1.92565. Okay, so next go for the seventh iteration. So the seventh iteration, so already we have seen this has been converged with the one decimal point. So x value is 2.42603, and y value is 3.57395, z value is 1.92604. So now can you observe that the root has been converged with two decimal places now. So if you get one more step, it is 8th iteration, then I think the root will be converged. So this is 2.42527, and y value is 3.57278, and z value is 1.92593. Okay, so now you can observe that the root has been converged. So this can be taken as 2.426. This can also be taken as 4.426. Okay, 3.57, 3.57, 1.92, 1.92. So the root has been converged. So I think you can stop here. This can also be taken as 1.926. Okay, so this can be taken as 3.573. Okay, and this is 425 only. So now we have seen that the rule has been converged in the 8th step. Therefore, the values of x is, what is the x value? 2.425. Y value is 3.573 and Z value is 1.926. Corrected to 3 decimal places. Corrected to 3 decimal places. Okay. So this is by what? This is for Jacobi iteration. This is for Jacobi iteration. For Gauss-Seidel also, we will be having the same iteration table, but there will be less number of steps, so that we can carry out, I think. So by Gauss-Seidel, okay. So please carry out this by Gauss-Seidel. So we will be having the iteration table. Again, the first iteration, the x values, y values, and z values. So this is in the first iteration, x value is 3.14815, y value is 3.54072, and z value is 1.91317. Okay. So in the second iteration, the x changed to 2.43218, y changed to 3.57204, and z changed to 1.92585. In the third iteration, x changed to 2.42569, y changed to 3.57294, and z is 1.92595. Okay. The fourth iteration, so it is again 2.42549, y value is 3.57301, and z value is 1.92595. Okay. See, z has been already converged. It is 1.92595, 1.92595. Whereas y value is also 3.573 we can take, and this also we can take it as 2.425. Okay. So this can be taken as 3.425, and this is 3.573, and this is 1.925. That is taken as 1.926. Okay. See the number of steps in the both the methods. In the Jacobi iteration, okay, in the Jacobi iteration we have taken 8 steps, whereas in the Gauss-Seidel we have taken hardly 4 steps. That means we can say that Gauss-Seidel converges twice faster than the Jacobi iteration. Okay, so we have taken hardly 4 steps here in the Gauss-Seidel, whereas in the Jacobi iteration we have taken 8 steps. Okay, and here only 4 steps. So therefore we can see that x value is again 2.425, and y value is 3.573, and z value is 1.925, corrected to 3 decimal places. Okay, so you can just give this table of iteration for both Gauss-Seidel as well as Jacobi iterations, provided initially you have to explain first 2 iterations. First 2 iterations you need to explain as we did in the previous example. See, first iteration and second iterations are explained, then third, fourth we have just mentioned the values by calculated by the calculator. Okay. In this method also, so we have solved by Jacobi iteration as well as Gauss-Seidel. For Jacobi iteration, we have taken x0 as 0, y0 and z0. So, but for Gauss-Seidel, we only take y0 and z0. For Gauss-Seidel, take y0 as 0 and z0 as 0. So here we don't want x0 in the Gauss-Seidel. In the Gauss-Seidel we don't want x0, we want only y0 and z0. Whereas in the Jacobi iteration we want all these three. We want all these three. Okay. So that is what the difference between Jacobi iteration and this is by Gauss-Seidel. Okay. So I think very sufficient examples have been given. So we have done 5 examples, each 5 examples, right? Yeah, example 5. So each example we had done by Gauss-Seidel as well as Jacobi iteration. We have done 5 examples and each example by Jacobi iteration as well as Gauss-Seidel. So therefore almost 10 examples we have covered. So we have covered sufficient examples on the Gauss-Seidel as well as Jacobi iteration method of solving simultaneous linear equations. So therefore I think we can conclude here. So we can conclude here. So this is end of unit 1. So this is end of unit 1. So in the next class we shall start unit 2, that is finite difference operators. Okay, thank you.